Hello everyone, welcome to the next lecture of bipolar junction transistors. By now we have started with the talking about the physical structure of the transistor, of the NP and PNP transistors. We talked about the modes of operation. We have discussed that in the cutoff mode, both of the junctions, emitter-based junction and collector-based junction needs to be reverse biased. For an active mode, emitter-based junction is forward biased and collector-based junction is reverse biased. For saturation mode, emitter-based junction is forward biased and collector-based junction should also be forward biased. We discussed in detail the operation of the transistor in the active mode. This was done for the NPN transistor, and today we are going to look at the PNP transistor, and we will realize that that it is very similar. We also developed this equivalent circuit models of the NPN transistor. Today we are going to do it for a PNP transistor too. In the last lecture, we talked in detail about the saturation mode of operation, where we see that when what will happen to the collector current as our transistor or collector to base junction enters from the reverse bias condition to the forward bias condition, right? It decreases sharply. And we developed this equivalent model, and then we did this analysis where we said that as the collector to base junction becomes forward bias, the base current will increase and the collector current will decrease. And so when this is happening, so this means that our beta gain factor will reduce. So we ended up seeing that the forced beta, or the beta in the saturation region, is going to be less than the beta in the active region, and that would be one condition for the how to determine the saturation region operation of the transistor. Okay, so today let's start with the PNP transistor. Okay, so here's a PNP transistor. Again, 3 terminals: emitter terminal, base terminal, and collector terminal. Right, we have a PNP transistor, so p-type, n-type, p-type materials here. Second important things, let's assume this operation for the active region when our emitter to base junction needs to be forward biased and collector to base junction needs to be reverse biased, right? Okay, forward bias, collector to base junction needs to be reverse biased. Okay, in order to forward bias this PN junction, now you will realize that we need to make the p-type material at a higher potential as compared to the base, which is n-type. Right, so this is emitter, this is base, this is collector. So we need to make sure that our emitter is at a higher potential than the base. And considering the diode model, we know that for the forward biasing, we can assume it to be around 0.7 volts. Then in order to make the collector base junction reverse biased, now since our collector is a p-type material, I want my base to be at a higher potential than the collector terminal. Collector terminal is again p-type. So you will notice that the polarities of these batteries are exactly opposite to the NPN transistor, because now we have complementary p and n-type regions for emitter, base, and collector regions. Okay, so now let's discuss what is happening in the operation. So once we forward bias the emitter to base junction, we are going to have over here, we're going to have a bunch of this p-type material, we're going to have a bunch of holes, right? And we're going to have a bunch of electrons. Again, our emitter is heavily doped as compared to the base. So what we are going to have is we're going to have a lot of, as we forward bias the emitter to base junction, we are going to have a lot of these holes that will be injected from the emitter to the base. At the same time, we're going to have these electrons that are present in the n-type base that will be injected from the base to the emitter. Okay, so what will happen to these holes that were injected from the emitter to the base? Some of these holes will be combined with these electrons and neutralize in a process known as recombination. Exactly the same thing is what's happening, except the charge carriers were complementary in the NPN transistor. Okay, so for a PNP over here, the holes that were injected from the emitter to the base, some of these holes will combine with the electrons in the base, which is an n-type, and will be lost or neutralized in a recombination process. Rest of these holes will be swept across this junction into the collector terminal, towards the collector terminal, right? So this is negative here. So these holes will be swept across it. So the current, so all of these holes that were started from the emitter and injected and into the base and then swept across the collector to base junction to the collector terminal will mainly constitute the collector current. And since our collector current is because of these holes, we can see the direction of the collector current is also reversed now. Okay. Another thing that you can see over here is this kind of a width difference. This width difference represents the difference of the number of the holes that were started with from the emitter region that came into the base, but then some of these holes over here, the difference of the width will be lost in the recombination process, and the rest of them went to the collector terminal or collector region. Okay, so let's look at the base current now. Again, base region will, or the base current will have two components. One component is this IB1, which is the number of the or injected electrons. Base is an n-type, so there's going to be a lot of these electrons. The base, these electrons will be injected from the base to the emitter region. So this constitutes IB1. And then we have lost some of these electrons of the base region in a recombination process. In order to supplement these electrons will be drawn from the external circuit, right? And so when these electrons will be drawn from the external circuit, that will constitute the current IB2. And so that is why you can see that the direction of the base current is also now in the opposite direction, IB here, going out of the base terminal. Again, you have an emitter current, which is because of the injected electrons from the base to the emitter and injected holes from the emitter to the base. So that is why your direction of the emitter current is also into the emitter terminal. So important thing to remember is operation is exactly the same. The regions are complementary, P and P, and in order to forward bias the emitter to base junction and reverse bias the collector to base junction, you need opposite polarity batteries to connect over here. All right. Let's look at the large signal models of PNP bipolar junction transistor, right? So we did the similar thing for an NPN transistor in very detail. So essentially these models are exactly the same over here for the PNP as well. We have an emitter terminal here, we have a collector terminal here, a base terminal here. The direction of the currents, you can find out the direction of the current for the emitter current going into the emitter terminal, for the base and the collector going out of the terminals, right? For the base going out of the terminal, for the collector going out, for the emitter going into the terminal. Okay. Now we know that, right, where is it? Okay. All right, so this is our collector current. And so we know that the collector current will be the same as a scaling current, e raised to power biasing voltage. Our biasing voltage is now opposite polarity, VEB. So I will write VEB over VT. So this is the collector current over here, which is represented over here. And we know that for a common base model, I can also write this common base model with IC equals alpha times IE. So this is also equals to alpha times IE. So if I will consider this equation, I can see that this is a voltage control current source. If I will consider this equation, I can see that it is a current control current source. So this is the current source that appears into the collector terminal, and now we have a diode that appears into the emitter branch, right? So this is the diode DE over here that appears, and this diode represents this emitter to base junction for a common base model, and the scaling current through this diode will be equals to IS over alpha. And how do we know that? We can replace this IC and alpha times IE over here. So we have alpha IE equals IS e raised to power VEB over VT. IA equals IS over alpha e raised to power VEB over VT. So this is the value of IE. So we can replace this value of the IE over here. So the scaling current that is flowing through this PN junction or through this diode will be equals to IS over alpha, right? While our IE will be equals to IS over alpha, VEB over VT. Okay, so this is the model for a common base model. Similarly, we can develop a common emitter model, which is exactly going to remain the same as the remain similar to the NPN transistor, right? So we have three terminals: emitter, base, and collector. Direction of the currents, you can see it. Again, this is our collector current, which is based on this biasing voltage, the scaling current, and the exponent of this biasing voltage. The biasing voltage of emitter to base junction, the polarity is opposite as compared to the NPN transistor. Now, if I am interested in finding out the value over here, this can also be represented by this. So our IC is equals to beta times IB. So considering this equation, so the collector we can see that this is a constant current, or this is a voltage control current source, and looking at this equation I can see that it's a current control current source. Similarly, now in order to model the emitter base junction while having a common emitter model, we ended up putting a diode into the base branch, which is represented by dB, right? So let's find out the value of the current IB, right? So we can find out the value of the current IB from here, right? So we know that IC equals IS e raised to power VEB over VT. Let's put the value of IC over here. So the IC will be equals to now beta times IB into this. So what we can see is the base current will be equals to IS over beta e raised to power VEB over VT. Now we can see that the base current has a scaling current of IS over beta. So this scaling current is appearing over here. So looking at both of these models, these are very similar models to the NPN transistor. The only differences are you can see that the direction of the currents. The other difference that you can see is the biasing potential, or the polarities of that biasing potential. These are the main differences. Otherwise, the operation of the PNP transistor is the same due to the complementary nature of the NPN regions and the majority charge carriers available. We're gonna require opposite polarity batteries to forward and reverse bias the collector base junction and the emitter base junction respectively. Similarly, our direction of the currents will change as well. Okay. So these are the large signal equivalent model for the PNP transistor. So if you have to develop a model, I hope the concept will be clear over here. So let's get to the next topic. What are the circuit symbols for the PNP and NPN BJTs or bipolar junction transistors? So here's an NPN transistor, here's a PNP transistor, base terminal, collector terminal, emitter terminal, and then you can see the symbol over here, this symbol, right? So this arrow, whichever the terminal will show this arrow, that terminal will be an emitter terminal. So this is an emitter terminal, this is an emitter terminal. So whichever branch is going to have an arrow, that will be an emitter terminal. Second important thing will be the direction of this arrow. Direction of this arrow will determine whether it is an NPN or a PNP transistor. And direction of the arrow will be the direction of the emitter current, right? Over here, I can see that this is emitter current coming out of the emitter terminal. This is the emitter current coming into the emitter terminal. So let's verify this. For a PNP transistor, our current goes into the emitter terminal. For a PNP transistor, our current goes into the emitter terminal. For an NPN transistor, our current comes out of the emitter terminal. All right, so the direction of the arrow will represent the direction of the current or emitter current, and the arrow terminal or the arrow branch will represent the emitter terminal, The rest of the two are the middle one is the base and the other one will be collector then. All right. So this is how we bias the transistor, the NPN and the PNP transistor to operate that into different regions, right? And let's assume over here that we wanted to operate these transistors into an active mode. This means that again, to operate that into the active mode, emitter to base junction needs to be forward biased, collector to base junction needs to be reversed biased, right? So this is emitter to base junction, collector to base junction. This is an NPN transistor, NPN. Okay, so if I have to forward bias the emitter to base junction, right? So this is the emitter to base junction, or the voltage that is required to forward bias the emitter to base junction. So I will make the base at a higher potential as compared to the emitter, and it needs to exceed 0.7 volts or equal to forward bias it for the emitter to base. So this was the emitter to base junction, and this was a collector to base junction. Okay. For a collector to base junction, our collector, in order to make it reverse bias, our collector needs to be at a higher potential, right? So our collector is N-type, and we are connecting it to the positive terminal of a battery, so it will become reverse biased. And we also saw earlier that since the collector to base junction area is much larger than the emitter to base junction area, so the biasing potential required to forward bias it will be less. If our base is at least 0.4 volts higher than the collector terminal, then our collector to base junction will become forward bias, and we will move from the active to the saturation region of operation for a bipolar junction transistor. Now over here, this is our collector to base junction, CB, and this is our emitter to base junction. Now we wanted to make sure that, so this is our PNP transistor, PNP. So we wanted to forward bias the emitter to base junction for active operation, right? So emitter or a p-type material is connected to the positive polarity, should be at a higher potential. And in order to reverse bias the collector to base junction, the collector is again a p-type, so we need to put that to an opposite polarity, right? So it should be connected to the negative terminal of the battery, or at a lower potential as compared to the base. Okay. Now let's look also at the potentials again very quickly for the NPN and the PNP bipolar junction transistor in the active and the saturation mode. This is a kind of a very simple diagram to explain the whole thing. Or the switching of the collector, or the voltage required the collector terminal to operate that terminal, or operate the transistor in between saturation and the active region. So this is a common emitter model. You can see it over here. We have a common emitter here. And then look at the base terminal. So in order to forward bias this emitter to base junction, we ended up supplying this 0.7 volts, right? So considering a real diode or a real PN junction model, we saw that it is approximately equals to 0.7 volts. So we can make a fair estimate that our emitter to base voltage over here, right? So NPN. So our VBE needs to be equal or greater than 0.7 volts to forward bias this emitter to base junction. Now let's look at what is happening at the collector to base junction, right? So we also know that in order to reverse bias the collector to base junction, so our collector to base junction is, we saw that, so our base is p-type. So when our base to collector voltage is greater or equals to 0.4 volts, it will become forward biased, right? Or it will enter into the saturation region. So this will be VB minus VC is greater than 0.4 volts. So I can further do this thing, 0.7 minus VC greater than 0.4 volts. So 0.3 volts will be VC. So our collector voltage needs to be greater than 0.3 volts to operate that into the active region, right? So this is what is happening over here, that in order to operate that into the active region, the collector voltage should be greater than the 0.3 volts, right? So our collector voltage should be greater than the 0.3 volts to operate that into the active region. Similarly, we can see it over here. As long as our collector voltage does not fall below zero point 0.4 volts compared to the base, it will remain in the active region. So similar analysis can be done for the saturation mode over here. Okay, yeah, so similar analysis can be done for the saturation mode over here, where our emitter to base junction is forward biased and our collector voltage is not allowed to rise above that of the base by more than 0.4 volts. Because when that will happen, our collector to base junction becomes forward bias and the PNP transistor will move from the active region into the saturation region. Okay. So our next is more like a very quick summary of the BJT current voltage relationships, right? So this is kind of a summary of all the equations. Here's our collector current. Right, sorry, this is the biasing voltage, right? So this is for NPN. You can also look it over here with the biasing potential. Our collector current depends on the biasing voltage value and the scaling current. Similarly, our base current has a scaling current factor. We determined that earlier, right? And the same biasing depends on the same biasing voltage. Emitter current, this value of the scaling current, same biasing voltage. What will happen for the PNP transistor? We just ended up replacing the opposite batteries to forward bias emitter to base junction and reverse bias the collector to base junction. Similarly, you have also seen all of these equations earlier. So this is a kind of a good summary slide to have if you are solving any example problems. This is a good summary slide to have all of these equations in one place. Vt is a thermal voltage value. If you remember the PN junction lectures from earlier part of the course, you know that its value is approximately equals to 25 millivolt at room temperature. There is one topic very quickly that I want to talk about is before we do one more example today on the circuit design. So one more topic that I want to talk about, but in this entire discussion of the PNP and the NPN operation of the transistors, we did not talked about the minority charge carriers or the thermally generated charge carriers. Right, we kind of, yeah, in all of these current flow discussions in the BJTs, emitter, collector, base, we were talking about the majority charge carriers, did not talk about at all about the minority or the thermally generated charge minority carriers. They are usually those current values, those those charge carriers that constitutes those reverse currents are very small. So we usually neglect them. However, I do want to mention about this collector to base current, or you're going to come across this collector to base reverse current, which is sometimes significant if you're doing a more comprehensive analysis. And what this O represents over here, so this ICB is the collector to base reverse current, and O is when emitter is open circuited. Okay, so let's see what this is. This collector to base reverse current is usually in nanoamperes range, and its value is sometimes comes out to be higher than the theoretically predicted value. It represents a leakage current. If you remember the p-n junction physics that we discussed earlier in the course, and the value of this reverse current, as we know, depends on the biasing voltages at the junctions, right? So for the collector to base reverse current will depend on the biasing potential of the collector to base junction, which is VCB here. Another factor that this reverse currents usually depend on, we know that it depends on the temperature. So for every 10 degrees Celsius rise in temperature, whenever there's a 10 degrees Celsius rise in temperature, the reverse current will double. Something to consider when you are designing these circuits for high power applications. All right, so let's do one more example today. So let's see, this is a circuit that is shown here, and it has a beta of 100. It has the biasing, VBE will be the biasing voltage of 0.7 when the collector current is 1 milliampere, and we need to design this circuit. Designing a circuit means that we need to find the value of the RC and RE so that a current of 2 milliamperes flows through the collector and a voltage of 5 volts appears across the collector, right? So we know that this is the base, this is the emitter because of the arrow, and this is the collector. Sorry, this is the collector. So this is the voltage at the collector, this is the voltage at the emitter. Another thing that we know the current at the collector is 2 milliamperes. So we know that this IC value is 2 milliamperes, okay? So if the value of the IC is 2 milliamperes, let's find out the value of IE and IB. So we know that the value of IB. So what is IB? IB is IC over beta. So IC is, what is IC? 2 milliamperes divided by 100. So we can find the IB. So it will be 2 milliamperes divided by 100. And IE will be equals to IB plus IC. We know that IE is the summation of the base current and the collector current. So if we put down all of these values, we see that our collector current is 2 milliamperes. We can find out the value of the IB from here, 2 milliamperes over 100, beta value is 100. Similarly, IE, the emitter current equals IC plus IB, which will come out to be 2.02 milliamperes, and the base current is 0.02 milliamperes. Right, okay, so even this is 20 micron amperes. So even if you look at all of these currents, right, so you have a base current of approximately 20 micron amperes, emitter current of 2 milliamperes, and the collector current of 2 milliamperes approximately. So the reverse currents from the collector to base junction is of the order of nanoamperes. So even for the very small base currents, the reverse currents are even thousands of times smaller. So that is why we usually end up neglecting it. Okay, so another thing that we know is that the voltage plus 5 volts appears at a collector. So this VC will be plus 5 volts over here. This VC is plus 5 volt. Okay, so let's design the circuit. We already know this potential, we know this potential, and we know the current flowing through this plant, so we can easily find the value of RC. Right, so we can find out the value of RC. So our RC can be found out as 15 minus VC over IC. So 15 minus VC is 5 volt over IC is 2 milliamperes. We can easily find out the exact value here, which will come out to be what is the value? Okay, so this will come out to be 5 kilo ohms, right? So this is our 15 volts, which is this power supply. VC is 5 volts, IC is 2 milliamperes, so the RC value will be 5 kilo ohms. Another thing to notice is that we want to figure out where the transistor is operating, so we can also look at whether this transistor is operating in the active mode or in the saturation mode. So how do we know that? By finding out whether the collector to base junction is reverse biased or not. So you easily know that, for example, the base voltage is 0 over here, right? And the collector voltage is 5 volts over here. So your collector voltage is much higher than the base voltage, and it's an NPN transistor, right? Since the collector voltage is higher than the base voltage, so this means that the collector to base junction is reverse biased and the transistor is being operated in the active mode of operation. All right, so the second thing that we want to find out now is our base to emitter voltage over here, VBE, right? So this is VBE. So base to emitter voltage, or the voltage that will appear across the emitter to base junction. So the one thing that is given in the question is the voltage that appears across the base to emitter junction is 0.7 volts, but this is the voltage that will appear when the collector current is 1 milliamperes. However, we know that our collector current is 2 milliamperes. So what will be the new value of VBE at collector current of 2 milliamperes? So in order to solve that, we can use this equation from the diode stepper. If you remember the PN junction again. So this is the equation. So over here, your V2 is the new value of VBE, and your V1 is the old value of VBE, and your VT is the thermal volts. I2 will be the new value, 2 milliamperes, I1 is the old value 1 milliamperes, or this is the value at which you have V1 volt, or this junction voltage that appears across it. So if you will solve this equation, the value of the VBE that we will get is 0.717 volts. Right, so since we know that our VBE is 0, so our emitter voltage will be minus 0.717 volts. Right, so the voltage that will appear over here, VE, will be equals to minus 0.717 volts. Okay, so considering that, we can easily use this to solve out our value of RE. So RE will be equals to VE, so this VE minus 15 volts divided by IE. We already know the value of IE, which is equals to 2.02 milliamperes. We already know the value of VE, which is minus 0.717 volts. So if we replace all of these values, we can find out the value of RE. Right, so VB is 0, this is VE, and similarly we can put down the values of VE minus 0.717 and IE 2.02 milliamperes, and our resistance will come out to be 7.07 kilo ohms. Okay, our last topic for today's lecture is this. I wanna very quickly show you the IV characteristics of the transistor. Right, so this is IC VBE characteristics. Here is my collector current, and here is the base to emitter junction voltage. So this is the potential or the voltage that will appear across the base to emitter junction. Here's a collector current. So collector current equals the scaling current, and it will depend on the biasing potential that is appearing at the emitter to base junction. Is e raised to power VBE over VT. Now, since we are considering the diode model, the real diode model, so the potential difference that we can generally assume it to be 0.7 volts. If we apply this potential, our emitter to base junction will become forward biased. This is an exponential model again here. Similarly, we know that, right? So this is our IC, and we know that our other equations are, if you will go back over here, right, our IB is IS over beta, and our e raised to power VBE over VT, and IE is IS over alpha e raised to power VBE over VT. So these are the scaling currents, and otherwise the relationships will be exactly the same, exponential, and will depend on the biasing potential. Right, so if I have to find out the relationship in between IB and VBE, it will be an exponential relationship. The only difference will be the scaling current, the magnitude of the scaling current. Similarly, IE versus VBE will also be exponential, except the magnitude of the scaling current. IB versus VBE will be exponential, except the value of the scaling current. All right, so this is what we said over here. Another thing over here is we just already talked about this, that in order to solve, so while you are solving all of these circuit problems, you can fairly assume that the biasing potential across emitter to base junction is 0.7 volts. And another important thing about the emitter to base junctions, the PN junctions, is this dependence on the temperature. We have a collector current over here, and again we have emitter to base voltage, and these are our exponential relationships, right, this one. But we know that the emitter to base junction, the current will depend on the temperature, and as our temperature is increasing, right, as our temperature is increasing, we see that the potential drop across that junction will decrease. So we have a kind of an inverse relationship over here. And for 1 degree rise in Celsius in temperature, right, for a delta T of 1 degree Celsius rise in temperature, our delta we will be 2 millivolts, a decrease of 2 millivolts. For a plus 1 degree Celsius rise in temperature, our junction temperature, base to emitter junction temperature, reduces by 2 millivolts. Okay, so this is the last topic for today. And then next week we will talk. We are going to do some more examples. We will also make some more models. Um, and we're going to do a lot of examples as well. I hope that that examples will help all of you to make these concepts more clear. Again, concepts are very important. I hope all of these concepts will help you not only just to solve the problems itself, but also to understand what is going on in the transistor, and yeah, fundamentally what is happening. Okay, so with that, I am going to finish up this lecture, and we're gonna talk in the next lecture. Thank you so much, and have a good rest of the day. Bye bye.